Bill Nye.
Okay, go.
Bill and I are out like Magic School Bus. Okay, guys, tell me, what is the ideal gas law?
PV equals nRT.
Okay. PV equals nRT. You guys know that very well. You're very acquainted. Okay. What if we wanted to solve just for P? What would I do?
Divide by V.
Okay. Divide by V. All right. So what I'm going to get here is pressure equals nRT over V. Now what I want you guys to see is that isn't N over V moles per liter? Oh, it's molarity. Right. Okay. So remember, in the last unit in kinetics, a lot of times instead of being given molarity, data in molarity, we were given data in pressures, and I said it's fine. You can use that because pressure is going to change just like molarity is going to change. So they're certainly proportional. But are they equal? No. Pressure is equal to molarity times RT. So what you'll notice in the formula that you used last night is this. Kp equals Kc for concentration or molarity times RT. And then did you notice that it was raised to the delta N?
Yeah.
Okay. The delta N is just because if you were to convert all of these pressures to molarities, remember you still have them raised to an exponent. So you have to kind of compensate for the exponents. Remember, the delta N was nothing more than number of gas product moles minus the number of gas reactant moles. If it is not a gas, what do you do? Right, you exclude it. You just ignore it. So you only look in your reaction for gases. So like for this one, if we had hydrogen gas plus iodine solid yields hydrogen iodide gas, if that was our reaction, then what would our delta N value be? Let's see. How many product moles do we have? 2. How many reactant moles do we have? 1. And so it would be raised to the first power. What if I got it hot enough to where iodine started out as a gas? Then, what would this be? 2. And so what would our exponent be? 0. And so this is a unique case. Yes, right, Sean. If you raise this to the 0 power, this is a 1. So this would be a unique case when Kp is actually identical to Kc. The number of moles are the same of gas. Okay?
The equilibrium that we form, that mean like there's equal parts gas, equal parts, or equal parts like H and I, and equal parts HI? What does that mean?
Okay, and that is the biggest misconception about equilibrium, okay, is that, here's the deal. If these were always exactly equal, then wouldn't your K always be like 1?
Yeah.
Okay, but K's aren't 1. They're like 5 times 10 to the negative 12, 5 times 10 to the negative 18, 36, 5. So here is the deal, and this is what's hard to understand. What is equal about equilibrium is not the amounts, it's the rates. Okay, so you start out with, let's say you start out with just reactants. What's the only thing that can happen if you just have reactants? You can form products. Once your products build up, if it's a reversible reaction, what can happen? Or what will happen? The products will do what?
Turn into.
They'll go back and make reactants. And so what happens is you have forward reaction going, reverse reaction going, and they're going to keep going at uneven rates until you get to the perfect balancing point for that reaction. Every reaction has its own unique balancing point, which gives them their own unique K value. Once you get there, then, does it stop? Does it stay still? What did we say yesterday?
Yes.
It keeps on going because we call it a dynamic equilibrium, okay? Not a static one. It doesn't just stop. So once it gets to that balance point, you'll constantly have reactant make product, but you'll have at the same time and at the same rate, product make reactant. So at that point, what is equal about equilibrium is that the rates will stay the same, so that equilibrium, that perfect balance, that equilibrium constant will be preserved.
So basically, at first, if the rates are uneven, that means they can move at different time lengths to get
Yes.
to one side. But once it reaches dynamic equilibrium, so it's the same exact amount of time to go from products to reactants or from reactants to products.
Exactly. Exactly. Okay? So that's the equal part of equilibrium. Not the amounts, but the rates once it gets there. Now, if you're at equilibrium and then you stress it out like we did yesterday, remember I added chloride and then it had to adjust, and then I added water and it had to adjust. If you stress it out, it's no longer at equilibrium, so then you're going to have unequal rates until it gets back to its equilibrium constant, and then at that point, it's at its dynamic equilibrium, and it'll keep on going. Jordan, does that make better sense? Yeah. Okay, and that helps, and it takes a while to get that concept down, because we hear equal, we're so used to law of conservation of mass. That's just where we go. That's where we go with it. Okay. All right. So, does anybody actually need me